Hi, in these sequence of videos we are going to be looking at magnets and magnetism. Starting off with this puppy, the humble bar magnet, moving right through to the EMF induced in a conductor due to cutting magnetic flux. Let's get started. Okay, in the fact that the getting the bar magnet out of the iron filings is a bit of a waste of time, so we just quickly skip through some GCSE revision. The key things you need to know are as follows. Number one, the field lines around a bar magnet have this sort of typical shape. You've probably seen it, if not you can look up on YouTube. But the key thing you need to really take away from this is that the field lines go from north to south, and they show the direction of the force acting on the north pole of a magnet. Second of all, the field lines do not have to leave the surface at right angles to the bar magnet like they do with electric field lines. They can just come off at any old direction. Okay, so that's the bar magnet. The density of the closeness to the field lines, the closer they are together, the stronger the field is at that point. Okay, and we call this idea of how strong they are, we describe that as the flux density. So here, these lines, we call these flux lines. And where there's lots of them, it's close, we have a strong flux density. Or high flux density, I should say, really. Okay, and that magnetic flux density is given the unit or the symbol B, and that is measured in Teslas. Okay, so where the field lines or the flux lines are close together, that's where the magnetic field is the strongest. Where they're more separated, if we took a space that size, put it over here, say, then there's not so many field lines there, so it's not as strong. Okie dokie. So this first key point is, rather than just being magnetic field strength at GCSE, we have to talk about magnetic flux density, units of Tesla. Okie dokie. Over to here, again with GCSE, you would realise that there is a magnetic field around a current carrying conductor. Now in this situation, the current is going to go around the blue circuit like such. As you can see here, it's coming out of the page. Out of this is square things like representing a page. If you take a pen, hold it in your right hand and put your thumb like such, your fingers will go round the conductor, the pen in a certain direction. If your thumb shows the direction of the current, your fingers will show the direction of the field. And as you can see from this, straight away, I've drawn my flux lines the wrong way around. There you go. Teaching straight away. Boom. So, think this through. There's my thumb coming up towards the camera, or up in this situation, my fingers go around the pen that way. So the magnetic field goes round in this direction. Okay, now things you need to know about this. This idea here is the right hand grip rule. Right hand grip. And in this situation, what we basically say is that the thumb, okay, is the current. Is the current, and your fingers, now here's where the test of my artistic skills. Here the fingers are going to go around in like that, there you go, and I suppose we'll give ourselves a full finger like that. So the fingers represent the direction of the magnetic field. Okay, that's the right hand grip rule. Now, it's worth noting at this stage that where the field is the strongest, the field lines are the closer together, and that is near to the conductor. As you get further away, these field lines get eccentrically further apart. Okay, and the field strength is directly proportional to the distance. Inversely proportional to the distance. So field strength around the wire is B is proportional to 1 over the radius, however far away you are. Okie dokie, moving on from that, we have this situation here. Now what I'm trying to draw here is a coil of wire that's looping, going in and out of the page. I haven't drawn what you can see from underneath, but with this looping round, you have what's called a solenoid. So this thing is a solenoid, and a solenoid is just a coil of wire that's carrying a current. Now, if you apply the right hand grip rule to each of these points of the wire, if you think at this particular point right here, it's coming out of the page, the wire is coming up and going up, so if it's carrying current, oh god, I'm trying to count the wrong way around here as well. It's going this way, like that. Okie dokie. So here's going, I don't know again, oh, excuse me. There we go. So it's going from long to short, so it's going around like that. Here the current's going up. Now if you were to apply the right hand grip rule, you'd have a situation where you have a little mini magnetic field going that direction, around like that. Of course, if you apply this one here, you'd have the same situation. And of course here it would be going up, and here we go in the opposite direction. So in the middle, they cancel each other out. So you actually don't get a series of concentric circles. The central parts basically cancel each other out on this. And so what you do get though is in the between the coils, inside the actual solenoid, inside the loop of it, you get a uniform field. And if you look at it from above, you get coming out of the ends, you get this typical field pattern, just like you do a bar magnet. So if you were to redraw this solenoid over here from above, and just say, here's my lines coming out, going in, coming out, going in, and sort of looping around the page like such. When you apply a field to it, when you apply a current side to that solenoid, you get a pattern just like you do inside a bar magnet there. Okay, next thing, if you get rid of this now, and think about what this field looks like if you're looking at the ends of it. So imagine our solenoid now, there it is, I'll just draw it like that. Quickly, if you imagine you're looking in at one end of it from this end here, and you're looking straight on it, what you'd see would be a circle like that. And if you were looking at it from this end here, you would see a circle like that. Now if the current is going round this way from looking at it this end, then if you're looking at it from this end, if this way is going anti-clockwise, then this end, if you're looking at it, will appear to be going around clockwise. Okay, so if the current, you can't see current flowing obviously, but the point is this: if you're looking at it from the end of the solenoid and the current's going around clockwise or anti-clockwise, we can predict, we can tell the direction of the magnetic field. So in this situation, we would have to do following the direction of the current. We can draw a shape like that, and that's roughly an N. And if you draw it like this, field lines like such, that's roughly an S. Okay, so from this, what you can say is if you're looking at the end of a solenoid, and the current from your particular viewpoint appears to be going around clockwise, then you're looking at the south pole. Okay, that's basically the south pole of that solenoid. And if you're looking at it at the where it's going anti-clockwise, it appears to be the north pole. So straight away we can tell quite a lot of stuff about magnetic fields. Now most of this should be GCSE revision, maybe not this bit, but that's the start of it. So this is just really magnetic fields in their most basic form.